Ok, va bene. Grazie agli organizzatori, prima di tutto, perché insomma, ho capito che questo è il primo seminario della nuova stagione autunnale di ISMAR, che come seminari adesso, almeno qui, riusciamo a fare in modalità ibrida. Ci sono circa 10 persone qua a Venezia in sala conferenze. It's a good point for us to be some people here in the audience and someone remotely connected from the other ISMAR offices, because as Oyvind knows, ISMAR is spread over different places in Venice. So just a brief introduction for this seminar. So we are hosting Oyvind Breivik from Norway Bergen, because we have some common project on extreme waves in the North Sea, basically. But Oyvind is not only head of division for meteorological oceanographic study at the Norway Bergen, but is also professor at the local university. So it's a great pleasure to host him here. So today's seminar will not deal about extreme waves, but more focus on nightcast, long-term they made for atmosphere waves and water level in the Norwegian and North Sea. Hopefully something we can also use for some ideas for us for the future. Thank you very much.
Thank you, Alvisa, and thank you. Let me start by thanking Alvisa and Luigi in particular for letting me spend 3 months here in ISMAR in Venice. So far, it's been very interesting, very enjoyable, and we've already struck up quite a good collaboration, and I'm expecting there to be more ideas coming. I've got no less than 3 PhD students who will be visiting over the next month and a half. So there is a broad range of overlapping fields of interest, not just in the field of extreme waves, but also when it comes to wave climate, but also in fact on pollution and microplastics. So there is a lot of common interest between ISMAR and the Norwegian Meteorological Institute. Perhaps I should take a couple of minutes just to explain what the Norwegian Meteorological Institute is. It is the Norwegian Met Office. So in other words, we are the ones who forecast the weather for Norway. We're also responsible for a lot of the operational oceanographic forecasting. So we deal, for instance, with emergency preparedness models for search and rescue, for oil, for drifting ships. And we do a lot of we collect a lot of wave measurements and a lot of the more traditional meteorological observations that weather forecast agencies typically collect. And we do a lot of not just operational modeling, but also things like what I'm going to present today, these hindcast products, which are really just climatological archives that you can use for whatever purpose you want. But if you need to know the weather on a particular day, for instance, there are only so many observations around that you can use. But if you put the observations into a model, you can get a continuous field, and you can then come up with a weather situation for a particular day. You can do the same with waves. You can do the same with water levels, so that you can go in and you can ask, so what on this particular day when northern Norway in 2011 was struck by a combination of high winds and from a rather unfortunate angle which coincided with spring tide. What exactly was the water level, and what was the sea state, and how strong were the winds when they hit Kabelvåg in this that you see here in this picture. So that's one of the uses for these hindcast archives. Another and perhaps more common use would be that you simply go in and you do the statistics and you ask, so what is the average wind speed in the North Sea, or what is the most extreme winds that you could expect in the North Sea? And that's of course of huge importance to a lot of people and a lot of different businesses and activities. So I'm going to try to motivate why we put together these enormous numerical simulations. They're very costly, they're very expensive to run and generate, and why it's important to do this, and why would we want to be interested in the past weather in the first place. So hopefully I will convince you that this is worthwhile. but let's start by looking at the geographical domain of our Hindcast archives. What you're seeing here is actually there are two different archives overlaid on each other. There is a red one and there is a blue one. The red one is the old one, which has roughly 10 kilometer resolution and is known as NORA 10. It's been around now we started work on that. It was one of the first big projects that I was involved in 15 years ago. The new is in blue, and that's the NORA 3. So you can see that the numbers 3 and 10, they typically then indicate a resolution. So we've gone from 10 kilometers to 3 kilometers resolution. If you think that sounds unimpressive, I can tell you that the difference in computational effort is something like 3 by 3 by 2 by 1.5. So then you can start to do the maths on how much more work that would be in the number of individual time steps in this model. And then to make matters even worse, we used to have a hydrostatic model. So that's an atmospheric model which doesn't care about vertical accelerations. And now we have an atmospheric model which does concern itself with vertical accelerations. So if you're interested, like Luigi is, in the Bora, for instance, you know that the Bora accelerates down the mountain slopes. So then you need to know something about the vertical accelerations. If you're over the ocean, that may not be so important. But one of the things we're hoping, and we're indeed seeing, is that at 3 kilometer resolution, you're starting to resolve features in complex terrain that are important for the local wind climate. So to summarize this, the new atmospheric part of this hindcast is on 3 kilometer horizontal resolution with 65 vertical levels. The lowest level is at 12 meters. The highest is at 10 hectopascals. I don't know if that tells you much if you're not atmospheric scientists, but just to give you an idea, at 5,000 meters, you've roughly gone down from 1,000 hectopascals to 5,000 to 500 hectopascals. So at 10 hectopascals, you're pretty high up, well above Mount Everest, to put it that way. Anyway, let's continue with the and not get too hung up on the details, but let's pause for a moment and just remember that so far we have now a continuous archive from 1990 until 2021, still counting. And the person who is responsible for working on this is one of my PhD students. And she is constantly babysitting this model to produce it. And it is so heavy to run that typically we can generate something like maybe 10 years, 12 years per year. So a year from now, we're hoping to have extended it back to 1979 or 1980. And that's sort of the beginning of the Era 5 reanalysis, which we use as our host. Okay. Let's continue, and let's try to outline the talk. I think I've already started. I will first now try to motivate hindcasting, why we do it. And in doing so, I will also start by defining what hindcasting is. And then I will go into a bit of details on the 3 different components, the atmospheric one, the wave part of the hindcast, and then finally the part which has been least investigated so far, which is the barotropic storm surge hindcast. So I'll leave that until the end. Okay, so in hindsight, why hindcast? Why do we do this? As I've already said, it's important because you may want to know what the weather and the waves were like on a particular day, but more generally, you would like to know the statistics. You would like to know 99% of the time, what kind of winds can I expect not to see? In other words, am I safe at a certain level, at a 99% level, or maybe at a 1 in 10,000 level? If you're running an oil rig, you would typically say, no, my level, I need to be safe in a 10,000 year perspective. In other words, they want a 10 to the -4 probability that they do not exceed a certain significant wave height or a certain strength in wind or so far. So we use it for a lot of statistics. And the advantage of going back in time is, of course, that you can reconstruct the past. You can't really know the future, but that's the obvious next step, is that you also want to know something like both Alvise and others have been doing recently, that you take a climate projection and you downscale that to your region of interest, and you say, what do I think that the climate is going to be like in the next maybe 30 or 50 years? That's the natural follow-up. But in order to do that, you typically want to have a baseline. You typically want to know what the past climate was like. And that goes for the atmosphere, that also goes for the waves, and it goes for water level. And there are a multitude of users of these hindcast archives. Here we're looking at a number of them. The wind turbine parks that are starting to crop up in the North Sea are heavy users of hindcast archives. What they need is, they need really detailed wind profiles. They need to know what is the typical wind profile from maybe 10 meters and up to maybe as much as 200 meters, because they need to know the typical wind speed at the hub height, but they also need to know the difference between when the wings are at their lowest most point and their highest point. What is the difference? What is the shear in the wind profile? So that's important for them. And of course, they would also like to know how extreme are waves in the area, because you want to know how much fatigue, how much wear and tear will there be on a wind turbine like this in typical conditions. That's a new and emerging thing, which is taking up more and more of our activities. More traditionally, this guy has been a typical customer of hindcast archives. What you're seeing here is something that you would never see in the North Sea. This is from the Gulf of Mexico in the upper right-hand corner. The platform that you're seeing was actually built, it was designed to do exactly what it does there, because it doesn't make sense to build platforms in the Gulf of Mexico so that they can withstand tropical cyclones. That would just be too many inches of steel. So what they do instead is that they evacuate them, and then every now and then they're unlucky and they keel over. In the North Sea, they take a different philosophy, because there you have extra tropical storms. They don't typically become so fierce as the tropical cyclones. So they build platforms so that they can withstand them. And if they are to withstand them, the really critical point would be what is known as the air gap. So the air gap is between the bottom of steel, the lowest part of the platform, and the crest of the wave. But obviously, that air gap, and if you're the offshore installation manager, if you're in charge of this platform, you would want that air gap to be comfortably big. You would want there to be no doubt that there is air between the tallest wave and the bottom of steel. And that depends basically on two things. It depends on the water level, and it depends on how tall the waves are. So both of these things are obviously an effect of the weather. If you have strong winds from the wrong direction, you can have both a high water level, as you are painfully aware of in Venice, and you can have, as opposed to the Venice Lagoon, which is very sheltered, you can have very tall waves for the same reason. You have strong winds, and if they come from the wrong direction, you have long fetch in the North Sea, and then you can have really tall waves. That's typically what you want. You want to know that if you're the offshore installation manager, you want to know that this air gap is comfortably big. And that may not necessarily always be so. I mean, this is a picture which was taken a few years ago. As a fun fact, Alvise, the lasers that we compare the stereo cameras to are placed on this footbridge between these two platforms. The one on the left, that's the Bravo platform, and the one that you can't see on the right, which connects with this footbridge, is called the Kilo platform, and that's where we have stereo cameras that Alvise is helping us make sense of. The average distance from the footbridge to the water level is about 22 meters. So you can see that it's very, very far from 22 meters right now in this picture. And in this picture, it's even less. You can see that you actually here you have white water coming up underneath the bottom of steel on this platform. So these guys in charge of the oil platforms are very, very aware of what they need. So they're actually very skilled, very good customers in that sense. They really push us. They really know what they need and what they want when it comes to these hindcast products. So even if I'm certainly not going to I'm not a big fan of continued oil production in general, but what I would say is that in the past 30 years, this industry has actually it's really made a difference in pushing us to understand various wave phenomena and also in general the wave climatology of the North Sea and the Norwegian Sea. The other I would say emerging field for hindcast archives is insurance payments. And I'm currently involved in a project which is called Storm Risk, which probably has a self-explanatory name. We want to look at the risk, the monetary risk, or the financial risk involved in other words, in losses due to various kinds of weather-related phenomena. And what you're seeing in the lower left-hand corner here is a pie chart which shows the amount of damage from avalanches, flood, and storms in Norway in the past 10 years, from 2010 until 2019. And then you see a tiny, tiny sliver here which says earthquakes, 0.0%. Norway is in a very, very calm, non-active geological zone. So that's not an issue. These numbers would look very different, I presume, for Italy. But what you can see here is that quite exactly half of the payments are due to storms. Storm surges make up something like 6%. That's the green part here. And so when you look at this, what you can see is that there are a few storms. Some of them, this one is unnamed, but there are a few which have been named in the past 10 years. And there are, you can attribute most of the payments to just a handful of storms in the past 10 or 20 years. So knowing the potential damage from individual storms is important, and that's something that these hindcast archives can also help us identify. So I'd say that this is one of the emerging users of hindcast products. And then back to this, coastal communities are also increasingly making use of hindcast data. And I mean, the combination with insurance payments is obvious. I mean, if you have damage to a coastal community, then somebody needs to step in and cover the damage. So now back to the technicalities of this. So my talk now will be divided into three, and I'll make sure that I don't go into all the details of this because I can go on at length, but I would like to give you a flavor of the three different components. They're very different numerical models. And I'll start with the atmospheric one. The point here is that for us, the most important thing is to try to get a realistic picture of the wind field. That's what to me is most important. Rainfall is also very important, but not so much in this particular study. That will come later. But I would like to draw your attention to the difference in average wind. This is the average taken over a month. It's the month of January 2011, but that's of little importance, the exact month. The point here is that on the left-hand side, you can see that the average wind speed taken from ERA 5, which is a global reanalysis, which is generated by the European Centre for Medium-Range Weather Forecasts, that we use as a so-called host. So we use that on the boundaries of our regional hindcasts. And you can see that the field is very smooth. Over the open ocean, for the winter of for the month of January 2011, you had 9 meters per second average wind speed. Over the mountains in southern Norway, you can see that it goes down to somewhere between 2 and 4 meters per second, and in the coastal zone, somewhere between 8 and 6 meters per second. It doesn't look totally unrealistic, but it's clearly a very coarse field. Then let's go and see what the old hindcast archive that we have been using now for the past decade and a half, that shows a lot more detail, because it's a 10-kilometer resolution, whereas ERA 5 has about 31-kilometer resolution. So there's a lot more detail added to it. But compared to the new 3-kilometer resolution model, you can see that even that amount of detail is nothing compared to what you get when you have a really realistic topography over this over southern Norway. And southern Norway is not as mountainous as northern Italy and the Alps and the Dolomites, but it's still, we have mountains going up to maybe 2,000 to 2,500 meters. So there's a lot of up and down, and we have narrow fjords with maybe a cross section of as little as 2 to 4 kilometers. So clearly, the resolution will matter, and it does. And so far, I haven't said anything about whether it's correct or not. So we'll get to that. But you can clearly see that the resolution makes a huge impact on the average wind field. Whereas over the open ocean, they seem to more or less agree. The wind speed is somewhere around 9 meters per second. The yellowish to orange color here is about 9 meters per second. The wind speed in NORA 3 may be slightly stronger than what you find in ERA 5, even over the open ocean, but they seem to be quite in agreement over the open ocean. But in the coastal zone, they're very different, and obviously in mountainous terrain, they're also enormously different. If we go into the details here, we can see that these differences are, this is the difference between NORA 3 and ERA 5. You can see the pale red here is about 0.5 meters per second, which means that ERA 5 is biased low by typically something like 0.5 meter per second over the ocean. So that's similar to what I showed in the previous figure for that 1 month. Over the western mountains, you can see, and over Iceland, it seems to be biased very low, if we believe NORA 3. Whereas on the eastern side, or you in the lee of Norway, over Sweden, it's actually overestimating the wind speed. So far, I haven't said anything about who is right and who is wrong. I'm now getting to that. In this particular snapshot over 1 month, black is the observations from an Arctic station. Blue is the it says windsurfer, but that's just because we have used different names for different projects. It's the same model. So blue is now the NORA 3 wind speed as it's going up and down. You can see that there's a couple of weather systems passing by, and green is now ERA 5, and you can see that ERA 5 is very, very weak in winds compared to, oops, something happened. It does that.
I mean, is this on the mountain or what?
This is a mountain station in the Arctic. It's near Longyearbyen in Svalbard. I could have picked other ones as well. So this is just to give you an idea that Even if we don't fully capture all the storms, you can see that even NORA 3 isn't able to fully capture it. There's an enormous improvement. But so far, this is quite anecdotal, and you shouldn't really trust me on this yet. So let's get to the details here, and let's see what this means in terms of mean error and mean absolute error. And what you're seeing then is that the upper curve here is from 2010 until 2016. So this is about 6 years that we've taken out. And you can see again the blue curve and the black curve, that's the NORA 3 versus the observations. And you can see that they tend to be closer to each other than the two other data sets. The ERA 5 is it's continuously underestimating for mountain stations. The mean error, likewise, is much smaller. So the blue one is almost unbiased. You want to be as close as possible to the black curve. And the mean absolute error, that's the random error, is also smaller for the blue curve than for the red and the green. This one, the last one, is something that you don't usually see, but I think it's quite an important measure. It says something about the standard deviation of your time series and compare that to the standard deviation of the observations. You want that to be the same kind of variability in your time series. You don't want a model which is flatlining. If you have something which is flatlining, it may on average be more correct than something which is going up and down. But what this is telling you is that the activity ratio of the model is similar to the activity of the real atmosphere. So in other words, there is the same amount of ups and downs that you find in reality. So the closer you are to the black line here, the better. So what you're also seeing then is that ERA 5 here is grossly underestimating the amount of variability in the atmosphere. And that's typical for a coarse model. Okay, I'm not going to go into all the details here. What I'm going to tell you very quickly now is that this measure, the equitable threat score, is telling you whether a model is doing okay at various wind speeds. You can use this for any variable you want, but in this case, it's the wind speed. So what you want is for this curve to be as high up as possible. It's doing okay. It's doing better than the two other models for all wind speeds above 3 meters per second. That's really what it's saying. So for mountain station, it's really outwitting the two other models. When it comes to maritime stations, you can see that these two are almost identical, the old and the new hindcast, but ERA 5 is lower. So it's a way of comparing the quality of the hindcast at various wind speeds, all the way from the weakest winds to the strongest winds. Okay, so quickly going on. This is again just telling you that if you're really concerned about the upper percentiles, the really strongest winds, and that's something that a lot of our users and customers are interested in, this is where they would start to really ask questions. Are you representing the 95th percentile, the 99th percentile correctly? So again, if you plot the, I think this is really a bit too coarse. Let me zoom in on this. If you compare the 95th percentile of the observations, that's in black, versus the NORA 3 in blue, you can see that I picked out the mountain stations here, and that's a bit selfish of me because this is where we really make this is where this archive is really coming into its own and really performing best. You can see that we're almost perfectly following the 95th percentile of the observations from 2004 all the way up until 2018. Whereas both the old hindcast archive in red and the ERA 5, which most people would have access to through the CMEMS product, no, the C3S Copernicus products, you see that they tend to be biased very low when you get up into the upper percentiles, and that's very important. It's really important if you want to do extreme value analysis. So that's another reason why these hindcast archives are useful. I think that's enough for the atmosphere. For the wave model, we would have liked to run a couple wave atmosphere system. and is really at the outset of the project. That's what we wanted to do. After a lot of back and forth, we decided that we couldn't really afford to do that this time. So we ended up doing a wave hindcast only. So in other words, we forced the wave model with winds from the atmospheric model, but there is no feedback. So in other words, we don't take we don't modify the roughness of the sea surface and give that information back to the atmosphere, which is something ECMWF have pioneered over the past, well, in the 90s, they pioneered that method, and it's proven to be important for medium range weather forecasting. In our case, what we see is that we get pretty good results, even with an uncoupled system. I want to focus on this part here inside the box, because that's the part that is really, that's the part that is being investigated with NORA 3 winds. The outer part is really just to create the sufficiently large boundary around this area. Because we also have, we also try to serve two different purposes with this wave hindcast. We also serve the Copernicus product with this. But focus on this black box here. This is where we have winds from the NORA 3 hindcast. One of the things we have found, and this is a paper that I'm putting together now, is that as you get towards higher and higher resolution winds, these winds also tend to become stronger. Stronger winds is something that it's good because it's realistic. We've seen that is realistic when we compare it to observations, but it's also a practical problem because wave models have traditionally been tuned to much coarser winds. They've been tuned to winds where the resolution is typically somewhere between 50 and maybe 150 kilometers. When you guys started out, your average atmospheric model had maybe 150 kilometer resolution.
More.
Yeah, maybe even more.
I think at 3 degrees in the Atlantic.
Yeah, yeah. So at 3 degrees, that would be roughly 300 kilometers. The synoptic systems are resolved, but you tend to underestimate the winds, the intensity of the winds. So at some point in the late 80s and through the 90s, wave models, first WAM and then WaveWatch 3, they were tuned towards these winds. They were tuned so that they would match the observations of the wave buoy observations using the winds provided by an atmospheric model which is coarse. That's fine, except when your atmospheric model is no longer coarse, then you start to get into trouble. And that's the practical problem that we found, and that we've been working now with Joanna Stanova and Jean Bidot on, is that what happens is that it is really as you get up towards 30 meters per second, that's when you really start to get in trouble. Then, especially an uncoupled atmospheric model, an uncoupled wave model will tend to go off on a wild tangent and produce way too high waves. You had a question, Luigi?
No.
Yeah. So what we did was that we took down what is known as the Charnock coefficient. As you get above 38 meters per second, you start to take down the Charnock coefficient. And without going into the details of that, what that means is that the drag coefficient is reduced. So in other words, the drag that the atmosphere feels from the waves, the drag that generates or creates the wave growth is taken down. So here what you're seeing is a comparison from two different locations of two different runs. The alternative run out is run with a reduction of this Charnock coefficient, and the control run is a run where we don't reduce the Charnock coefficient. And you can see that if you compare, especially if you compare the yellow, if you compare the yellow to the pink in the Faroe Scotland channel. If you compare these two curves, you can see that you're really reducing the drag coefficient quite substantially as you get up close to 30 meters per second. And there is mounting evidence that this is something that you, one way or another, you need to do this as you get up into this range. And there is a string of papers over the past 15 years to indicate that the drag coefficient this is a physical mechanism. It's really starting to flatten out and then maybe even going down again as you get into well, close to 35 meters per second. So how does that then manifest itself? Well, on the left here, we just have the wind speed, just for comparison, from a number of different observing locations. So you can see that the winds are pretty good. They're from NORA 3. They're quite unbiased. You've got the observations on the x-axis, and you have NORA 3 winds on the y-axis, and you can see that they're pretty close to the 45-degree line. So they're pretty unbiased. They may be a little stronger, or there is some indication that they're a bit too strong when you get up to around 30 meters per second. But there is not really a huge difference or overestimation. When you look at the control run from buoys in the North Sea and the Norwegian Sea, you can see that they're really starting to take off. So this is if you don't reduce the Charnock coefficient. You can see that observations indicate maybe.
We're talking about wave
now we're talking about waves. So this is the wind that is driving it. Now here we're quality checking the wind that is driving the wave model. And in the upper right-hand corner, you've got the wave model where you don't reduce the Charnock coefficient. And now you're seeing that at something like 12, 13 meter significant wave height observations, you typically overestimate by a number of meters, like maybe 4 or 5 meters. And this becomes even worse as you go up towards 14, 15 meters significant wave height. You can see that you're really overestimating. Whereas if you do take down the Charnock coefficient, that's the lower figure here, you can see that there is still an overestimation, but it's much reduced to what it is in the control run without. So this is from a 2-year control run, which we use to assess whether this was a sensible approach. And then after that, we decided on this formulation, and we continued with the whole hindcast period.
Sorry, may I ask?
Yeah, sure.
So in the uncoupled system you have, so you mean that the atmosphere does not feel any reduction of the drag?
No, there is no feedback from the wave field in this hindcast.
In case of you have a coupled system, should also that reduction improve the atmosphere?
Yeah, it should. It should, but as you can see, the
benefit of the listener. Can you repeat the question?
Yeah, I'll try to repeat Alvisa's question. So what Alvisa said was, if you had a fully coupled system where the atmosphere would respond to the wave model, to the roughness of the wave model, then that should also improve the quality of the winds in the atmospheric model. And the answer is yes, it should. And the follow-up to that answer is that, but it's not really that necessary. As you can see from this, we're already doing a pretty good job even without the coupling, and that's one of the reasons why we decided to go ahead with an uncoupled system, because on this resolution, 3-kilometer resolution, and relatively rapidly in a not too big area, the impact of going to a coupled system is not as big as it would be for ECMWF, where you run 10-15 day forecasts, where you have much more time to develop these feedback mechanisms. So the feedback just doesn't have time to really kick in. Anyway, so we've seen the improvement here. We think we have a system which is working well. Yep.
That is control, and that is
alt is the alternative run. So control is the control run where we don't reduce the let's call it the drag coefficient. Technically it's called the Charnock parameter, but for all intents and purposes, it is a way of reducing the drag that waves impose on the wind. And the alternative is when we start to fiddle with it. And we see that the alternative is doing a much better job. It comes much closer as you get into the high winds. For the low winds, it doesn't really make a difference. You can see at 2 to 3 to 4 meters significant wave height, they're both doing perfectly fine. It is when you get up into the high winds. Yep.
Are you showing here for the wind just a station on the sea? Or
yeah, a few locations, only maritime locations. Yep, yeah, exactly. Good point. These numbers of observations are about the same, 141,000. I think they're from the same location, so these are co-located wind and wave measurements. Okay. This is just to give you an idea of, once you have this data set, you can then, of course, you can go in and you can ask, so what's the 99th percentile in this domain? And in our case, we see that we have a 99 percentile of something like 9, almost 10 meters significant wave height south of Iceland. And this is quite, I mean, this is quite uncontroversial. We know that this is the area, one of the harshest locations in the world in terms of wave climates. So this corresponds well with what we know already. So I just included it here to give you an idea of what's the kind of sea state that you can expect less than 1% of the time. If you were dropped at random in the North Atlantic or in the Norwegian Sea on a random day, what's the probability? In that case, the probability should be 1% that you would see 9 meter significant wave heights. Okay, finally, the storm surge part, and that's the least explored part of this. The two previous, the first, the atmospheric part was published and accepted in August. The wave part is, I'm about to submit it actually a few days from now. This part is just in its infancy. And what you're seeing here is a barotropic ocean model. So in other words, it's an ocean model where you don't worry about the salinity and the temperature. In fact, you don't even worry about the three-dimensional structure of the ocean. You just say, all right, let me see how the surface elevation will respond to changes in pressure and wind field. And there are essentially there are two ways that the atmosphere can change the water level. The first is that if you imagine the atmosphere as something pushing down on a water balloon, the heavier you push on a water balloon, the more you're going to squeeze it and it's going to swell up in other places. So that's the inverse barometer effect. If you increase the pressure by 1 hectopascal in the atmosphere, you reduce the water level by 1 centimeter. You're probably familiar with this in Venice as you live with this, but it means that if there is on average on the globe, the average pressure is 1,013 hectopascal. It means that if you have a storm coming through which has 970 hectopascal, you should expect 43 centimeters higher water level just from the inverse barometer effect alone. But there is another effect, and that is the Ekman transport. I've been told by Gigi that Ekman transport in the classical sense may not be so important for the Adriatic Sea, because the sea is narrow enough that really it's just a wind pushing the water in front of it. But in the North Sea is wide enough that when we have low pressure centers coming in, the Ekman transport pushes water 90 degrees to the right of the wind. That's due to the Earth's rotation and the friction against the sea surface. So the Ekman transport is the other side to this. So if we look at the map here of the North Sea and Norway, typically what happens here on the west coast of Norway where I live is that you have a combination. You have a low pressure center coming in, so the pressure is already low. So that means that the inverse barometer effect will tend to give you a higher water level. But then the wind is also pushing because the wind is blowing from the southwest. In fact, the rain hat is even called a southwester because that's usually where the shit weather is coming from in Northern Europe. And so when we have weather from the southwest, typically then the wind will push water up against the coast of Norway. So then you have a double whammy. You have the inverse barometer effect, and you have the Ekman transport. So for the coastal city of Bergen, where I'm from, that means that these colorful houses that you may have seen, which is called Bryggen, which is one of the tourist attractions, will typically then almost be underwater. There will be water on the doorsteps at least. So that's typically what happens with storm surges. So then what we want to do here is that we want to take the detailed 3-kilometer winds that we have and force a 4-kilometer, in fact, ocean model. And the reason we've chosen 4 kilometers is it's not really of any importance, but it's because it coincides with an operational forecast model that we have. So we just took the model we had and we just used the winds and we forced it. And this is a super fast model. It's 2-dimensional. So compared to the monstrous 3-dimensional atmospheric model, which has to take all the vertical accelerations into account and all that, this one, you can blast through the whole 25 years in like 2 days or something. So it's really a breeze. You just plug it into your supercomputer and off you go. So the hindcast itself is super cheap and fast to produce. So we're just sitting around waiting for my PhD student to finish her atmospheric wind and pressure fields, and then we do it. Anyway, so with these two effects, and then with the Kelvin waves that go like you can actually see them in this picture. You can see how this is actually the tidal motion. In this case, we don't really include the astronomical tides, but in this picture we did just to show you. You can see how you have high water level, low water level, high water level, low water level, high water level, and low water level. So that's just the astronomical tide going around the North Sea with in a anti-clockwise manner like this. So this is low tide, high tide. So 6 hours later, this part here is going to come south here, and then so on. It goes around the North Sea basin. And when you have pulses of wind setting on the Ekman transport, you have very similar effects. You have, for instance, the big disaster in 1953, the huge storm surge in the North Sea that caused a lot of damage on the eastern coast of Britain and in the Netherlands. Was caused by this kind of a wind field where you have a low pressure system sitting in this area, and where you have winds blowing from the north and then pushing water up against Scotland, and that builds up this wave which then goes down along the coast of the eastern coast of Britain. So anyway, in our runs, we don't include the astronomical tides. We expect those to be known, and we have good control of those. Of course, there are many ways to calculate them from coastal stations or offshore platforms. So what we're really interested in is just how extreme do these surges become. And we've done 2 runs so far. We've done one where we just use Era 5 winds and Era 5 pressure, just as kind of reference. How much worse does it get when we use the high resolution winds from NORA 3 compared to using Era 5. So when we do long runs, in fact, this is not even a really fair comparison, because this run is longer than this run, because we're still waiting for this one to finish the same period. So this one is just from 2002 until 2019, whereas this one goes all the way back to 1980 2019. But what you can see is that the maximum here storm surge is 3 meters, just 3 meters in the 40 years from 1980 until 2019 with Era 5, and you get to 3.6, so you add another half a meter or so when you use the NORA 3 winds. But I have to say this is preliminary work because we haven't completed. We've started comparing against observations, but we haven't really completed that yet. But the preliminary results are very promising. It seems they're actually very good. So I think with that, this is just giving you the total range. So what is the total difference between the lowest, because obviously when you have storm surge, you can also have the opposite. If you have a super high pressure system, which is pushing down the water level, you must expect there to be particularly low water level. So what is the maximum difference that you can find anywhere in this domain? And it's 5 meters. That's huge. Obviously, that won't happen like from one day to the next, because one will be a high pressure situation, the other will be a storm situation. But the question is one for instance, for engineers and people constructing harbors, what is the total range that you have to accommodate, so to speak, just due to the weather's effect? And that range in the German Bight is suggested to be around 5 meters. That's quite a lot. This is without the tides, exactly. So you have to add the tides on top of that. Perfectly right.
The period is different.
The period is different, that's true. So we expect this to become even worse, obviously, than if we add another 20 years from 1980 until 2002 to make it comparable. It should become even worse. Yeah, that's true. All right, so I think that's my final slide. This is just to show that with a data set like this, or actually with any data set of this kind, you can of course do the usual tricks with extreme value analysis. You can take your data set, your time series, and you can apply the usual generalized extreme value distribution, or you could use a generalized Pareto distribution, and you could say something about what you expect the 10 to the minus 2 or 10 to the minus 4 probability of return value to be of this parameter. And in that case, we see that we're starting to look into storm surges on the order of 4.5, 4.6 meters based on the data that we've generated so far. Okay, I think that brings me to the conclusions. I've presented the atmospheric hindcast, which is really, that's the bulk of the work, because that's where all the hard work is. Then the one wave hindcast is also expensive, but not anywhere near as expensive as the atmospheric hindcast. And then we have preliminary results from the storm surge hindcast. What I think is nice about this is that we will make all these data available online. Some of the data are already available online, so the atmospheric data set is already sitting there. The wave data as well are already sitting there. The reason we have different names for it is simply that we've had different funding streams, so we need to give them different names, but it's really all part of the same project. But and the storm surge data will also become available. All right.